Welcome everyone to this online talk about our latest paper, Architecture-Aware Synthesis of Phase-polynomials for NISQ devices. I am Arianne Meijer and I carried out this work with Ross Duncan at Cambridge Quantum Computing in Cambridge. So in this talk, we will first give a basic introduction to phase-polynomials and how they can be synthesized in an architecture-agnostic manner. However, as many of you are aware, current quantum devices have explicit constraints regarding which two qubits can interact with each other. So we'll briefly discuss the current methods of synthesizing phase polynomials that abide by these architecture-imposed constraints. In particular, we describe the methods currently used in the two compilers, Ticket and Stack. Then we explain and describe our newly proposed algorithm with a small example and experimental results against those compilers on current hardware. And lastly, we summarize and evaluate our results. So what is a phase polynomial? Well, a phase polynomial is a class of quantum circuits that only consists of C0 gates and Z rotations. So these circuits have the property that their unity matrix has a sum over path form with only two variables, the function f of x and the basis transform A. For completeness, the vector x describes the qubits in the circuits, and the function f of x describes on which combination of these qubits, denoted by the Boolean y, basically which combination of these qubits need to be XORed together, so at which parities need to be obtained before rotating it f hat degrees over the z-axis. So, and then the basis transform A describes which parities needs to be obtained at each qubit in the output. Okay. So this math is a bit dry, and so let's use diagrammatic reasoning. I mean, this is QPL after all. So in ZX calculus, we can draw the Z rotation gates and the C0 gates like this. So this is Z rotation. This is the C0 gate. Then we can draw each term of f of x, right, in the phase polynomial like a phase gadget, where alpha, this alpha, is this f hat y that we saw on the previous slide. And each gadget is connected to a qubit like this with a green spider, if and only if the x and the y of this particular index are 1, right? Okay. So given this notation, we know from Kauton et al. That we have these rules that explain how you can compose and decompose these phase gadgets. So on the left here, it shows how you can remove a green spider from a phase gadget by placing a C0 on either side. And given this rule, it can easily be shown that you can do the opposite way. That the opposite is also true. And this right rule, it shows that if you have a phase gadget that's only connected to a single qubit, then that's equivalent to just the Z rotation gate that we see here before, right? Okay, and that's what we're going to be using for the remainder of this talk. So a straightforward approach to phase polynomial synthesis is to then simply synthesize each phase gadget in the phase polynomial one by one using this recursive definition, as was previously proposed by Kauton et al., also presented last year. However, doing this naively will generate a lot of redundant C0 gates, and this needs to be optimized away. But of course, if you have a good optimizer such as Ticket, it isn't necessarily a bad thing to do. Alternatively, you can attempt to synthesize all phase gadgets together such that we can track the effects of synthesizing one phase gadgets on the remaining phase gadgets. And this approach is used in stack, and is also what our algorithm is based on. So let's just look what this matrix representation means in terms of ZX diagrams. Okay, so suppose we have a phase polynomial f of x, this one, and the base transform is identity just for sake of ease. Then we can write each term of f here as a phase gadget in the ZX diagram over here, right? And then the matrix representation that we're using is basically the concatenation of all these y vectors that you basically don't see because they're zeros and ones, but they basically say whether the x, which qubit is actually present in the term in this phase polynomial. So here you don't have x1, you do have x2, you do have x3, so you have this y factor, and then you concatenate all of this together. So you get this binary matrix representation. Okay, so interestingly enough, these ones and zeros in the matrix here, they correspond directly to the absence or presence of a green spider in this ZX diagram, which is really cool. But this is also natural because of the construction of both the diagram and matrix. But note that the order of the terms in F is arbitrary because these are pluses, right? Which is also true for the ZX diagram because these are all green spiders, so they commute. So the order of these phase gadgets is also arbitrary, but in normal math, shuffling around the columns of a matrix results actually in a different matrix, but our ZX transformation actually preserves the meaning of the diagrams, and that's why we like to explain this algorithm in terms of ZX diagrams, but in reality, our algorithm uses the matrix representation, and no real graph-like diagrammatic reasoning is used in the algorithms themselves. So now we have this ZX diagram. So what we can do now is place two C-knots here at the front. And we do that because they cancel each other out. So this is literally the same diagram we just placed two. And then we can use the rewrite rules that we saw a few slides earlier to push this rightmost C-knot to the right through all of the phase gadgets. So we use our rewrite rule, right, in the reverse order from there to there, then in a normal order from there to there, this one and there. There you can just see that these green spiders, they commute, so you can just push it through to the right, and then only connectivity matters, so you can move this one to the right and this one to the left, and you get this final matrix. And now what you can see here is what happened in terms of our matrix. Here is an elementary row operation. So we basically added this row to this one modulo 2, right? This is a binary matrix. So we added this row and we got that row, right? So that was really cool. And we will use this property later to pick which C-knots we want to synthesize. Now, those of you more familiar with ZX calculus see that this last diagram can be simplified even more. So we have our phase polynomial, our representation, we push the C-knot through, and now we have these trivial phase gadgets, right? So a phase gadget that's only interacting with a single qubit on is the same as the Z rotation on that qubit that we saw that before. So we can basically make this entire thing into a Z phase, and we can do that for alpha 2 and alpha 4. And then because these green spiders commute, we can push everything to the left, and it leaves us a smaller phase polynomial with only alpha 1 and alpha 3. Now, and then in the binary representation, you also see that what happened is we have these columns with only a single 1 in them, and they get removed because those phase gadgets have been synthesized. And this property we're going to use to reduce the synthesis problem into a smaller one. Okay. So how do we synthesize a phase polynomial such that it can be directly run on a given quantum computer's architecture? So C-nodes are only allowed between certain qubits, which is specified beforehand and can be described in a connectivity graph. Usually, the connectivity constraints of a target device are completely ignored using synthesis and only to be dealt with later during routing. Although this will result in a suitable circuit, this could introduce many unnecessary swap gates, making the circuit less optimal. So alternatively, National proposed an adjustment of a well-known synthesis algorithm called Grayson, such that every forbidden C-node is replaced with a sequence of allowed C-nodes during synthesis. And this improves the synthesized circuit with respect to the architecture agnostic synthesis followed by routing. However, the heuristics that are used in this algorithm are based on architecture agnostic rules, right? So phase gadgets might be synthesized in an order that is optimal for full connectivity, in other words, without constraints, but this ordering might be suboptimal for a specific connectivity graph. So instead, we propose a phase polynomial synthesis algorithm that is natively architecture aware. And this is the main idea behind our algorithm. So we start with our binary matrix representation of our f of x, and we call this matrix P. So first, we synthesize all the phase gadgets that are only acting on a single qubit, as these are trivial since they only require a single C rotation gate to be placed. And the columns corresponding to the synthesized phase gadgets can then be removed from the matrix representation as seen before in our example. So next, we pick a non-cutting vertex from the connectivity graph G, such that it can be removed without disconnecting the graph. So our goal is to remove this qubit, which is only possible if the corresponding row in the matrix is full with zeros. Luckily, we can split our matrix into columns where the row has zeros and columns where the row has a 1, right? And then we can recurse on columns with zeros and remove the qubit from that subproblem already. And by recursion, the submatrix will be synthesized, and we can focus on the remaining rows, which has a 1 in every column. So, and we want to remove all of those ones, right? So we pick a neighboring qubit in the connectivity graph. So this, if we do a C-node between those, that one is allowed. And we pick this neighbor such that it has most ones in its row, right? So we place a C-node with the chosen qubit as the control and the neighboring qubit as target, such that the target row is added to the control row and most ones are turned into zeros. In case that the chosen neighbor is a row full of zeros, this does not work because we're adding zeros to ones, right? So we're not getting any progress. So instead, we place an additional C-node in the opposite direction, effectively swapping the two rows, and then you've immediately removed all of your ones, and you can remove that qubit, which is what we wanted. So that's great. So after placing a C-node, we check if one of the columns has become trivial, because then we're done with it and we can synthesize it, just like in the first step. And again, we split the row and recurse on the zeros first to try and remove the remaining ones from the row once more, before recursing on the columns with ones and trying again. And lastly, we synthesize the basis transform A using Steiner-Gauss algorithm that I presented last year at QPL. But you can also use a similar algorithm. For example, the one from National, and there's a group in Bayesian that has an improved algorithm, which is really cool. Okay, so again, a quick example, right? This is the same phase polynomial we had before. Just going to ignore the basis transform. We're going to just keep that at identity, and we have this fake quantum computer architecture, which is basically a line of 3 qubits, and those are the only qubits we can place. Okay, so in this phase polynomial here, we see that the phase gadget alpha 4 is trivial, so we can synthesize it with the technique described before, and we move it to the front. And then we pick our non-cutting vertex with either the most ones or the most zeros. So this is a non-cutting vertex, and this is a non-cutting vertex. They have the same amount of ones and zeros, so it's trivial which we pick. So we, at least they're both allowed. In this case, we pick x1 arbitrarily, and we split our matrix into P0, this one is the first column, and P1 is the remaining columns. And then note that from P0, we remove this top 0 because that was our on our x1, and we're going to remove that for our subproblem. And we recurse on this matrix first. So we have this, and for completeness, I will show the entire ZX diagram and see what that does. So we have our smaller graph and this matrix and this diagram. And we're going to, again, pick a non-cutting qubit with either most ones and zeros. Well, there's the same ones and zeros. They're both non-cutting. So we can pick either of them, and we arbitrarily pick x3 with neighbor x2, and then place the C0 with control x3 and target x2. So that's this one. And so we push that through, this changes. And then we can synthesize alpha 1, which is cool. And we're done with our recursion here, because this matrix is, this row, right, is trivial, can be removed. We have no matrix anymore. So we're done with that, and we go back to synthesizing the remaining matrix. Now what you can see is that this is our P1 before, this is our P1 now. So synthesizing this P0 matrix also changed our P1. But that's what we want. So we have our new P1, right? And again, we do the same thing. We previously picked x1. So that's cool. So now we have to pick a neighbor. And we only have one neighbor. So that's x2. And we place the C0 with control x1 and target x2, which is this one. Push it through. And again, we split our matrix into this row, this column, and this column. And then we first recurse on the columns with zeros. That's this one. So again, we have the same matrix. We do the same thing, right? We arbitrarily pick the same qubit, and therefore the same neighbor, and place our C0, push it through, synthesize alpha 2. Awesome. And we only have one column left. So again, we already picked x1. So we need to pick a neighbor, which is only one neighbor, place the C0, and then recurse on the columns with the zeros, and then recurse on the columns with the ones, which is empty. So we get, again, the same matrix. We arbitrarily pick a qubit just to show that it can be the other way around. For a change, we'll pick the other one. We pick x2 with neighbor x3, and we synthesize of 3 right there, and that is our synthesized circuit. Now, usually what remains to be synthesized is the basis transform, but in our case it's identity, so it's trivial, no gates needs to be placed. But in case that the basis transform is not identity, we would need to synthesize this, and as optimization, we can push these rightmost C-nodes here into the transform and synthesize them together such that these C-nodes here can also be optimized. And for completeness, here's the pseudocode of our algorithm. Note that we split up our recursion into 2 different recursive functions, a base recursion step and a once recursion step. So the once recursion step is called when we already have picked a row to reduce, and we're just picking neighbors to reduce that, right? And place a signal gate. And in the base recursion step, we don't have a row yet, so we pick one and we split, and we call the corresponding functions. Mainly did that to make the pseudocode a bit more legible, hopefully. So for those of you who like a longer look, please read the paper. And if you're watching on YouTube, you can pause here. But it is basically the formalized version of what I have shown you before. And of course, you're all curious about how our algorithm holds up against the current state-of-the-art compilers on real devices. So we tested our algorithm against 2 compilers, Ticket and Stack. These are the only 2 compilers that I know that I can also synthesize. And so we randomly generated 20 different phase polynomials with different numbers of phase gadgets, right? So got 20 with 1 phase gadget, 20 with 5 phase gadgets, etc., all uniformly sampled. And we tested these phase polynomials to be synthesized on either the 16-qubit Rigetti Aspen or the 20-qubit IBM Singapore. I know that these, again, are different circuits, because this is a 16-qubit circuit and this is a 20-qubit circuit. Okay. And we also ran some qubit and phase gadget scaling experiments on fictional devices, and that can be found in the paper's appendix in case you are interested. So these are the results for the 16-qubit Rigetti Aspen device. So on the left, you see the number of C-nodes that were synthesized by the different methods. In the middle is the C-node depth, and on the right is the runtime in seconds. So I note that all of the numbers are the averages over the 20 random circuits that we picked or generated. So the blue line, that's our algorithm. The green line is stack, and the orange line is ticket. So you can clearly see that our algorithm generates a similar amount of C-nodes to stack here, maybe a little bit more, but you can see in the C-node depth that it is actually performing a lot better. And notice that this is an exponential scale. So these are quite big differences. So our algorithm is slightly better at parallelizing C-nodes than stack, which is nice. And additionally, we get these results without really compromising the runtime of the algorithm. Note that the tickets performance is the worst of the 3 in this case. It's because it synthesizes the phase gadgets 1 by 1, so it doesn't have this optimization thing going on. But the good performance of ticket here at the one with the single gadget case is probably caused by optimal placement of ticket, because ticket's really good at that. And here you have similar results for the 20-qubit Singapore device from IBM. And you can actually see exactly the same trend. So same CNOT count, better CNOT depth, similar runtime with respect to stack. And of course, better than ticket in this case. So in conclusion, we proposed a new natively architecture-aware heuristic algorithm for synthesizing phase polynomials with current and near-term NISQ devices in mind. This algorithm performs comparatively or better than the current state-of-the-art compilers without compromising the runtime of the algorithm, which is really nice. The algorithm mainly improves the parallelization of the CNOT gate with respect to the used baselines. And although this is, of course, desired behavior, it is worthwhile to investigate the effects of crosstalk between these parallel CNOT gates, because if it's just going to increase the error, that would be a shame. And moreover, the algorithm might benefit from better type-based strategies when two or more qubits or neighbors fit the selection criteria. And we've seen that a lot with the example that basically we were picking arbitrary qubits, although that's mainly caused by that is a very small graph, so there aren't a lot of options in a very small circuit. Lastly, we would like to extend this technique to synthesize a larger class of quantum computers, such as Pauli exponentials. And of course, for those interested, the source code and the raw results can be found on the Cambridge Quantum Computer GitHub page. Links over here. Thank you for your attention.